So before anything else, I would like to greet a pleasant afternoon to each and everyone, especially to our dear instructor, Ma'am Steph. Good afternoon, Ma'am. And by the way, let me introduce myself first. I am Honelyn. So for today's report, together with my co-reporter, Kimberly and Cecile, we will tackle about the cluster analysis and implementing clustering with Weka and R. So, but before we proceed, let me read first the chapter objective of this lesson. So first, to comprehend the concept of clustering, its applications and features. To understand various distance metrics for clustering of data. To comprehend the process of key-means clustering. To comprehend the process of hierarchical clustering algorithms. And last, to comprehend the process of DB scan algorithms. So, introduction to cluster analysis. So, when we say cluster analysis, it is an unsupervised learning technique which does not require a labeled data set. So, clustering is also defined as grouping a set of similar objects into classes or clusters. So, in other words, during cluster analysis, the data is grouped into classes or clusters, as shown in figure 7.1. The record within an intra-cluster have high similarity with one another but have high dissimilarities in comparison to two objects inter-cluster. So as you can see in the figure, an intra-cluster distances are minimized, while on the other hand, an inter-cluster distances are maximized. So application of cluster analysis. So we have 8 application of cluster analysis. First is marketing. Marketing is in clustering helps marketers find out distinctive groups among their customer bases, and this knowledge helps them improve their targeted marketing programs. Second one, land use. Clustering is used for identifying areas of similar land use from the database of Earth observation. The third one is insurance. So clustering is helping for recognizing cluster of insurance policyholders with a high regular claim cost. Fourth one, city planning. It also helps in identifying clusters of houses based on house type, geographical location, and value. The fifth one, earthquake studies. So clustering is helpful for analysis of earthquakes as it has been noticed that earthquake epicenters are clustered along continent faults. Sixth, biology studies. Clustering helps in defining plant and animal classifications, identifying genes with similar functionalities, and in gaining insight into structures inherent to populations. 7. Web discovery. Clustering is helpful in categorizing documents on the web for information discovery. Last but not the least, fraud detection. Clustering is also helpful in outlier detection applications such as credit card and fraud detection. So this let's proceed to the desired features of clustering. The first one is scalability. Algorithms should be capable of handling small as well as large datasets smoothly. So during the clustering, algorithms should be able to work efficiently with data sets of varying sizes, from small to very large, without a significant drop in performance. Second one, ability to handle different types of attributes. Algorithms should be able to handle different kinds of data, such as binary, categorical, and interval-based or numerical data. So clustering algorithms should be versatile enough to handle different types of data attributes, including binary, categorical, and interval-based or the numerical data. The third one, independent of data input order. So the result should not be dependent on the ordering of input data. So the result of clustering should remain consistent regardless of the order in which the data points are presented to the algorithm. The fourth one, identification of clusters with different shapes. So algorithms should be capable of identifying cluster of any shapes. So clustering algorithm should not be limited to finding only spherical or convex shaped clusters, they should be able to identify clusters of various shapes, including non-convex or irregular shapes. Next is the ability to handle noisy data. Usually, database consists of noisy, erroneous, or missing data, and algorithm must be able to handle this. So in real-world data sets, often contain errors, outliers, or missing values. Clustering algorithms should be robust enough to handle noisy data without significantly affecting their performance. Next is high performance. It is desirable that the algorithm should need to perform only one scan of the dataset. So ideally, clustering algorithms should be designed to minimize the number of times they need to scan the entire dataset to reduce computational cost, especially for datasets. The next one is interpretability. Result of clustering algorithms should be interpretable, logical, and usable. So therefore, clustering results should provide meaningful and interpretable insights that can easily understood and used by analysts or decision makers. Next is ability to stop and resume. So for a large data set, it is desirable to stop and resume the task as it can take a huge amount of time to accomplish the full task and breaks may be necessary. So therefore, for a large data sets or computational intensive tasks, clustering algorithms should allow the user to pause and later resume the process to accommodate interruption or resources constraints. Lastly, minimal user guidance. So algorithms should not expect too much supervision from the analyst because commonly the analyst has a limited knowledge of the data sets. So clustering algorithm should be designed to require minimal input or supervision from analysts, as analysts may have limited knowledge of the data sets or the optimal clustering structures. Let's proceed to the distance matrix. So a distance matrix is a function d of x and y that specifies the distance between elements of a set as a non-negative real zero. So distance matrix, also known as distance measures or similarity measures, are mathematical formulas or rules used to calculate the distance or similarity between two objects or data points. So let us first tackle the first distance, which is the Euclidean distance. So Euclidean distance is mainly used to calculate distances. So the distance between 2 points in the plane with coordinates x and y and a and b. So according to Euclidean distance, formula is given by Euclidean distance of x and y and a and b is equal to the square root of x minus a times 2 plus y minus b times 2. So for example, the Euclidean distance between points of -2 and 2 and -2 and -1. So we have 2 points here. Let's call them A and B. First is the point A, which are -2 and 2 and +2, and the point B are +2 and -1. So point A and B is calculated using formula Euclidean distance. So let x and y represent the coordinates of point A, which are -2 and +2, and let A and B represents the coordinates of point B, which are +2 and -1. So let's calculate their differences first. So Euclidean distance is equals to the value of x, which is the -2, and the value of y is equals to 2, and the value of a is 2, and the value of b is -1. So equals to the square root of -2 minus 2 times 2 plus 2 minus -1 times 2. So -2 minus 2 is equals to -4 times 2 plus Positive 2 minus negative 1 is equals to 3 times 2. So negative 4 times 2 is equals to 16 and 3 times 2 is equals to 9. So we have the square root of 25. And the square root of 25 is equals to 5. So our Euclidean distance now is 5. The second distance is Manhattan distance. So Manhattan distance is also called L1 distance. It is defined as the sum of the lengths of the projections of the line segment between the 2 points on the coordinate axis. So Manhattan distance is also called a city block distance because like Manhattan, it is the distance a car would drive in a city laid out in a square blocks. So for example, the distance between 2 points in the plane with coordinates x and y and a and b. So according to the Manhattan distance formula is given by Manhattan distance of x and y and a and b is equals to x minus a plus y minus b. So using the formula of Manhattan distance, we can calculate the similarity distance among first field. So using the data in the table above of person 1 and 2, we can calculate the Manhattan distance. So let x and y represent the attributes of person 1, which are 30 and 70, and let a and b represents the attributes of person 2, which are 40 and 54. So using the formula of Manhattan distance, since the value of x minus a plus the value of y minus b. So the x value now is represents 30, y value represents 70, a value represents 40, and b value represents 54. So Manhattan distance is the value of x, which is 30, and y, the value of y, which is 70, and the value of a as 40, and the value of b as 54. So is equals to the value of x minus the value of a, which is 30 minus 40, plus the value of y, that is 70, minus the value of b, which is 54. So 30 minus 40 is negative 10, plus 70 minus 54 is 16. So we have 10 plus 16, 26. So the Manhattan distance now is 26. So last distance, the Chebyshev distance. It's also called as chessboard distance because in a game of chess, the minimum number of moves required by a king to go from one square to another on a chessboard equals Chebyshev distance between the centers of the squares. So the Chebyshev distance measures the greatest absolute difference between corresponding coordinates of 2 points, making it a useful metric for problems where movement can occur in any direction. So formula of Chebyshev distance is given by Chebyshev distance of R1 and F1 and R2 and F2 is equals the maximum of R2 minus R1 and F2 minus F1. So this time we will going to calculate the person 1 and 3. So using the table above of person 1 and 3, so let R1 and F1 be the variables of person 1 and R2 and F2 variables of person 3. The value of R1 now is equals to 30 and the value of F1 is 70, the value of R2 is 80 and the value of F2 is 50. So equals to the maximum of the value of R2 which is 30 minus the value of R1 which is 80 and the value of F2 is which is 70 minus the value of F1 which is 50. So the maximum is equals to 50 and 20. So we have here 50 and 20. So its maximum is equals to 50. So our Chebyshev distance now is equals to 50.
Major clustering methods or algorithms. So clustering methods or algorithms can be categorized into five categories, which are given as follows. Number one is partitioning method. It constructs random partitions and then iteratively refines them by some criteria. 2. Hierar- Hierarchical method. It creates a hierarchical decomposition of the set of data or objects using criteria. Density-based method. It is based on connectivity and density functions. Grid-based method. It is based on a multiple-level granularity structure. And the last is model-based method. A model is considered for each of the clusters and the idea to identify the best fit for that model. So later on, we will further discuss these methods one by one with their corresponding steps. The categorization of clustering algorithms is shown. Now let us understand each method one by one. So partitioning clustering. Clustering is the task of splitting a group of data or dataset into a small number of clusters. Okay, so for example, the items in a grocery store are grouped into different categories like butter, milk, and cheese are clustered in dairy products. So those are qualitative kind of partitioning. A quantitative approach, on the other hand, measures certain features of the products. In the partitioning method, we cluster objects based on attributes into a number of partitions, as what I've exampled earlier. So while the k-means clustering is an important technique which falls under partitioning clustering. So k-means clustering. Okay, so in the k-means clustering algorithm, n objects are clustered into k clusters or partitions on the basis of attributes where k is less than n and k is a positive integer number. Okay, so in simple words, in k-means clustering algorithm, the objects are grouped into k number of clusters on the basis of attributes or features. So by that, grouping of objects is done by minimizing the sum of square of distances, a Euclidean distance between data and the corresponding cluster centroid. Working of the K-means algorithm. The working of K-means algorithm can be illustrated in 5 simple steps as given. So the first step is start with a selection of the value of k where k is equal to number of clusters. In this step, the k centroids or clusters are initiated and then the first k training samples out of n samples of data are taken as single element clusters. So each of the remaining n to k training samples are assigned to the cluster with the nearest centroid, and the centroid of the gaining cluster is recomputed after each assignment. Step 2. Creation of distance matrix between centroids and each pattern. In this step, distance is computed from each sample of data to the centroid of each of the clusters. The heavy calculation involved is the major drawback of this step since there are k centroids and n samples. The algorithm will have to compute n multiplied by k distances. Step 3. Assign each sample in the cluster with the closest centroid minimal distance. So now the samples are grouped on the basis of their distance from the centroid of each of the clusters. So if currently the sample is not in the cluster, then switch it to the cluster with the closest centroid. When there is no movement of samples to another cluster anymore, the algorithm will end. Step 4. Update the new centroids for each cluster. So in this step, the locations of centroids are updated. So update the location for each centroid of this cluster that has gained or lost a sample by computing the mean of each attribute of all samples belonging to respective clusters. Step 5. Repeat until no further change occurs. And lastly, here in step 5, you have You just have to return to step 2 of the algorithm and repeat the updating process of each centered location. So until a convergence condition is satisfied, which is until a pass through the training sample causes no new changes.
Starting values for K-means algorithm. Normally, we have to specify the number of starting seeds and clusters at the start of the K-means algorithm. We can use an iterative approach to overcome this problem. For example, first select three starting sets randomly and choose three clusters. Once the final clusters have been found, the process may be repeated several times with a different set of seeds. So we should select the seed records that are at maximum distance from each other or as far as possible. If two clusters are identified to be close together during the iterative process, it is appropriate to merge them. I- Issues with K-means algorithm. There are numbers of issues with the K-means algorithm that should be understood. Some of these are: first, the result of the K-means algorithm intensively depends on the initial guesses of the said records. Second, the K-means algorithm is sensitive to outliers. Thus, it may give poor result if an outlier is selected as starting seed record. Third, the K-means algorithm works on the basis of Euclidean distance and the means of the attributes values of intra-cluster objects. Thus, it only suitable for continuous data as it is restricted to data which there is the notion of center or centroid. So sometimes during clustering, the values of one attributes may be small as compared to others attributes. In such cases, that attributes will not have much influence on determining which clusters the objects belongs to, as the values of these attributes are smaller than other attributes and hence the variations within the attributes will also be small. Two techniques to convert the attributes. So in the case of normalization, all the attributes are converted to a normalized curve for a range of 0 and 1. The problem of normalization is an outlier. If there is an outlier, it will not tend to crunch all the outlier values down towards the value of 0. In order to understand this case, let's suppose the range of students' marks is 35 to 45 out of 100. Then 35 will be considered as 0 and 45 as 1. And the students will be distributed even between 0 to 1 depending upon their marks. But if there is one student having marks 90, then it will act as an outlier, and in this case 35 will be considered as 0 and 90 is 1. Now it will crunch most of the values down towards the value of 0. In this scenario, the solutions is standardization. So in the case of standardization, the values are all spread out so that we have standard deviations of 1. So generally, there is no rule for when to use normalization versus standardizations. However, if your data does not have outlier, use standardizations, otherwise use normalization. Using standardization tends to make the remaining values for all of the other attributes fall into similar ranges since all attributes have the same standard deviations of 1. Hierarchical clustering algorithms. Hierarchical clustering is a type of clustering analysis which seeks to generate a hierarchy of clusters. It is also called hierarchical cluster analysis. Hierarchical clustering methods build a nested series of clusters in comparison to partitioned method that generate only a flat set of clusters. So there are two types of hierarchical clustering, that is agglomerative and divisive. So what is a nested series of clusters? It is often referred to as hierarchical clustering is a method of organizing data into hierarchy of clusters within clusters. Agglomerative, or this is also called as bottom-up approach. In this approach, each object is clustered by itself at the start and its nearby clusters are repeatedly combined, resulting in a larger and larger clusters until some stopping criterion is met. The stopping criterion may be specified number of cluster or stage at which all the objects are combined into a single large clusters that is the highest level of hierarchy as shown in the figure 7.10. So in this approach, each data point starts at its own cluster. So then the algorithm repeatedly combines as the two closest clusters into a large clusters until all data points are grouped together in a single clusters at the top of the hierarchy. So the second one is the top-down approach, which is divisive. So, in this approach, all objects start from one cluster, and partitions are performed repeatedly, resulting in a smaller and smaller clusters until some stopping criterion is met, or each cluster consists of only objects as it is shown in this figure. So, in contrast, the divisive approach starts with all the data points in a single cluster. It is then recursively divides these clusters into smaller clusters. The procedure of clustering. So, first one is each item is allocated to a cluster. So, for example, if there are n items, then there will be n clusters. So, each cluster consisting of just one item, assume that the distance between the clusters are same as the distance between the item they contain. So, the second one is identify the nearest pair of clusters and merge that pair into a single cluster. So, that now we will have one cluster less. So, third one. Now, the distance between each of the clusters and the new clusters are calculated. The fourth one. Repeat each steps 2 and 3 until all items are merged into a single clusters of size n. As this type of hierarchical clustering merge clusters recursively is they're known also as agglomerative. Once the complete hierarchical tree is obtained, then there is no point of grouping n items in the single cluster. You just have to cut a k long distance. So let's understand the working of agglomerative clustering by considering the following row data in figure 7.11. So this method generates the hierarchy of recursively combining clusters from the individual items. So for example, there are 6 items R, S, T, X, Y, and Z. So the first step is to identify the items to be combined into a cluster. So normally the two closest elements are taken on the basis of the chosen distances. So when the tree is cut at a given height, it gives a partitioning clusters at a selection position. In this case, cutting the tree after the second row process cluster R, S, T, X, Y, and Z as shown in figure 7.12. So cutting the tree after the third row will produce clusters R, S, T, and X, Y, Z, which is called as coarse clustering. So with a smaller number of clusters, but which is the largest in size. The rule of linkage matrix. So it is required to compute the distance between clusters by using some metrics before any clustering is performed. These metrics are called linkage metrics. So it will be beneficial to identify the proximity matrix consistence of distance between each point using a distance function. So first is the importance of linkage. So in single linkage hierarchical clustering, the shortest distance between 2 points in each clusters is considered as the distance between two clusters. So, for example, the distance between two clusters R and S to the left is equal to the length of the arrow between their two closest points as is it is shown in this figure 7.13. So, complete linkage. So, in complete linkage hierarchical clustering, the longest distance between 2 points in each cluster is considered as the distance between two. So, for example, the distance between cluster R and S is equal to the length of the arrow between their two farthest points as shown in this figure. Average linkage hierarchical clustering. The average distance between each point is one cluster to every in the other cluster is considered as the distance between two clusters. So, for example, the distance between two clusters S and R to the left is equal to the average length of each arrow connecting to the points of one cluster to the other as it is shown in this figure. Example of single linkage hierarchical clustering. So let's perform a hierarchical clustering of some Indian cities on the basis of distance in kilometers between them. So in this case, single linkage clustering is used to calculate the distance between clusters. So the distance matrix with the sequence number of M0 is shown. So the nearest pair of cities is Srinagar and Pahalgam as the distance between them. So these cities are combined into a single cluster called Srinagar Pahalgam. Then the distance is calculated from this new compound object to all of our other objects. So in case of single linkage clustering, the shortest distance from any object of the cluster to the outside object is considered as the distance from the compound object to another. So therefore, distance from Srinagar Pahalgam to Delhi is picked up at to 842. So now the level of the new cluster is M2. So at the level of M1, the minimum distance of Jammu Amritsar in the distance matrix is 202. So in the distance between Jammu and Amritsar, so Jammu and Amritsar will be merged into a new cluster called Jammu Amritsar with new L. So at the level of M2, the minimum distance between Jammu, Amritsar, and Patiala in the distance is matrix is 235. So the distance between Jammu, Amritsar, and Patiala, so Jammu and Amritsar will be merged with Patiala into a new clusters. At the level of M3, the minimum distance of Jammu, Amritsar, Patiala, and Delhi is in the distance matrix of 267. So the distance between Jammu, Amritsar, Patiala, and Delhi. So Jammu, Amritsar, Patiala will be merged with Delhi in a new cluster. Then finally, the last two clusters are merged at the level 235. The whole procedure is outlined in this figure 7.16. So the major weaknesses of agglomerative clustering methods are given as follows. First, agglomerative clustering methods do not scale well as they have a high time complexity at least O(n) squared, as the algorithm will have to compute in times and distances. So where n is the number of total objects. And the second one, there is no undo mechanism to undo what has previously done. Density-based clustering. So, density-based clustering algorithm perform the clustering of data by forming the clusters of nodes on the basis of estimated density distributions of corresponding nodes in the region. So, in density-based clustering, the clusters are dense regions in the data space. So, these clusters are separated by regions of a lower object density. So, a cluster is defined as a maximal set of density connected points. So, neighborhood. So, neighborhood is an important term in used in DBS or data density based spatial clustering of application with noise. So, it represents objects within a certain radius of from a centroid types object. So, the high density neighborhood results if an object contains in a less minimum point of objects in its neighborhood as it is shown in the figure. So core. So a point is a known as core point if it has more than a specified number of minimum points. So within neighborhood. So these points must lie at the interior of a cluster. So a border point is a point if it has a fewer minimum points within neighborhood, but it is in the neighborhood of a core point. So a point is a noise or outlier point if it is neither a core point nor a border point. The concept of the core, border, and outlier is illustrated in this figure 7.20. So So DBS can definitions of clusters is defined based on the concept of density reachability. Generally, a point of Q is directly density reachable from a point of P if it is not more distance than a given distance. So however, one may consider that P and Q belong to a same cluster if point P is surrounded by unnecessary many points. So, as shown in the figure 7.21, if P is a core point and point Q is in a neighborhood E of P, then we can say that the point Q is directly density reachable from point P. Following other important observations that can be shown in this figure 7.21, point P is directly density reachable from point core point P. Point Q is not a core point as it has only 3 nodes in the neighborhood while minimum points is 4. Therefore, P is not directly density reachable from point Q. So, thus, density reachability is asymmetric. So, to further understand the concept of directly and indirectly density reachable, let us consider the figure 7.22. So, as shown in this figure, following some important observations, so we have here the point P2. It is a core point as it has more than 7 points within its neighborhood and point P is directly density reachable from it. So we have here point P2 is also a core point and a point P2 is directly density reachable from it. So point Q is also a core point and point P1 is directly density reachable from it. So here we have here from P, P2, P1, and Q form a chain. So point P is indirectly density reachable from point Q because P is not a core point as point Q is not a density reachable from it. So point P has 6 nodes in the neighborhood while minimum points values is 7. So it is important to notice that the relations of density reachable is not symmetric. The DBSCN algorithm. So after understanding of concepts of neighborhood, core, border, outlier points, and density reachability, DBSCN algorithm can be summarized as it's given as follows. So first, find the epsilon neighbors of every point. So and identify the core points with more than minimum neighborhood. And second one is find the connected components of core points of the neighborhood graph, ignoring all non-core points. Second, third one is assign each non-core point to nearby clusters if the cluster is an epsilon neighbor, otherwise assign it to the noise. So we have here the algorithm the BS-CAN algorithm advantages. So first one is it is not required to specify the number of clusters in the data at the start in the case of a DBS-CAN algorithm. The second one is it requires only two parameters and does not depend on the ordering of the points in the database. So the third one is it can identify clusters or arbitrary shape. It is also able to identify the clusters completely surrounded by a different clusters. The fourth one is the DBSN is a robust to outliers and has a notion of noise. So we also have the weakness of DBS-CAN algorithm. So we have here the disadvantages. First one is the algorithm is sensitive to the parameter. It is difficult to identify the correct set of parameters. The second one is the quality of the DBSC and algorithm depends upon the distance measures like a neighborhood and minimum points. And then the algorithm cannot clusters data sets accurately with varying density of a large difference in densities.
So now let's proceed to the implementing clustering with Weka and R. So the chapter objectives of this lesson is to apply the key means algorithm in Weka and R language, to interpret the result of clustering, to identify the optimum number of clusters, to apply classification on unlabeled data by using clustering as an intermediate step. So, as discussed earlier, if data is not labeled, then we can analyze this data by performing a clustering analysis, where clustering refers to the task of grouping a set of objects into classes of similar objects. So in this chapter, we will apply clustering on Fisher's iris dataset. And we will use clustering algorithms to group flower samples into clusters with similar flower dimensions. These clusters then become possible ways to group flower samples into species. So, in the case of classification, we know that the attributes of classes of instances, for example, the dimensions and classes were already known to us for the iris dataset. So our goal was to predict the class of an unknown sample as shown in figure 8.1. So we use the flower sepal length and width and the petal length and width as the specific attributes for this. Based on flower dimensions and using these three, we can identify an unknown iris as one of the three species such as setosa, versicolor, and virginica. So in clustering, we know that attributes for the instances, but we don't know the classes. So for example, we know the flower dimensions for examples of the iris dataset, but we don't know what classes exist as shown in figure 8.2. So therefore, our goal is to group instances into cluster with similar attributes or dimensions and then identify the class. So in this chapter, we will learn what happened if we don't know what classes the samples belong to, or even how many classes there are, or even what defines a class. So, so the advantage of using this data set is that we can compare the results of our clustering algorithm with the labeled data to judge the accuracy of our clustering algorithm. So since Fisher's iris dataset is already labeled, we will first make this dataset unlabeled by removing the class attribute, like for instance the species column. Then we will apply clustering algorithm to cluster this data on the basis of its input attributes, like for example sepal length, sepal width, petal length, and petal width. So as depicted in figure 8.3, the advantage of using the dataset is that we can compare the results of our clustering algorithms with the labeled data to judge the accuracy of our clustering algorithms. Like for example, Anderson classified each of the samples. So after clustering the samples, we can compare the results of clustering with the assigned classes in the original dataset. So clustering Fisher's iris dataset with a simple k-means algorithm. So now let's apply clustering on Fisher's iris dataset using Weka's simple k-means algorithm. So as shown in figure 8.4, since Fisher's iris dataset consists of samples belonging to three different species in the dataset, we will specify the num cluster to be 3. So the num cluster is kanisha. And then to help us interpret result, we'll set display std_debs to true so that we can see the standard deviation for the instance clusters of assignments. So for clustering, as we are not doing any training or testing of dataset, so we will select use training set, so kani siya, in cluster mode, and we also want the store cluster for visualization, kani siya. So as discussed earlier, for clustering, data should be unlabeled. So let us ignore the label attribute as shown in figure 8.5. So the species class attribute during application of the clustering algorithm by using ignore attributes and selecting class in the select items dialog. So next is handling missing values. So for missing numerical attributes, the missing value is field filled in by the average value of all the other values of the attributes. So when you have missing values in a numerical attribute, like for instance, age, income, temperature, and etc., a common approach is to fill in these missing values with the average or mean value of all the other known values for the specific attributes. So while on the other hand, for nominal attributes, the missing value is replaced by the most commonly occurring nominal value for attribute. So for nominal attribute, like for example, color, category, city, and etc., handling missing value is a bit different. In this case, you typically replace the missing value with the most commonly occurring nominal value, or also known as the mode for that attribute. So, so the result analysis after applying clustering. After applying the simple key-means clustering algorithm, we see the centroids of the three clusters and standard deviation for the sample values in each cluster as shown in figure 8.6. So for the results, we can verify that the key-means clustering algorithms identify three clusters of data having 61 instances for first cluster, 50 instances in second cluster, and 39 instances in third cluster. Since we are using the iris dataset, we know that there are three clusters, such as Setosa, versicolor, and Virginica. So having 50 instances each, thus, out of three clusters, one cluster has been identified perfectly while there is shifting of 11 instances from one cluster to another, because identified count of cluster is 61, 50, and 39 as shown in the figure 8.6. So, kanisha. So to compare the results given by the clustering algorithm with the actual clusters, we select the classes to cluster evaluation in cluster mode and rerun the clustering algorithm as shown in figure 8.7. So using this, we can get more information on where we can put each iris sample. So kana mga naka-highlight o mga naka-label. So from the confusion matrix in figure 8.7, it can be observed that all the setosa fall into a distinct cluster, like for example cluster 1. So we also see that the algorithm got most of the versicolor and virginica. So from the confusion matrix in figure 8.7, it can be observed that all the setosa fall into a distinct cluster, like for example cluster 1. We also see that the algorithm got most of the versicolor and virginica right in cluster 0 and cluster 2. We also see that the algorithm got most of the versicolor and virginica right in cluster 0 and cluster 2, respectively, but some of the versicolor and virginica did get mixed up with each other. Like for instance, 3 versicolor fall into the virginica cluster and 14 virginica fall into the versicolor cluster. So by specifying the num cluster to value 3, we can analyze that the simple key-means algorithm did a pretty good job of distinguishing between the different iris species. So we got 17 samples out of 150 samples that were classified wrongly according to Anderson classification. So the cluster assigned by the clustering algorithm can be visualized across any of the input attributes. So for example, figure 8.8 shows that the visualization of clusters along with the plot axis selected as petal length and petal width, jitter may be increased to see all the samples. So the samples which are classified correctly are shown by cross symbols, and wrongly classified samples are shown by squares in figure 8.8. So as we discussed earlier, Setosa got classified correctly and ended up in the right cluster. But we have some errors for versicolor and virginica, as indicated by the square boxes If you right click on any point of the plot, you can find out more about the associated sample. So kanang naka kani. So in figure 8.9, let us consider the plot of petal length versus petal width as shown in figure 8.9. So through visual examination, it can be analyzed that some of the versicolor instances that have been identified in the Virginica cluster, while it appears that on the basis of their petal length versus petal width, they should be identified directly. And similarly, there are some Virginica instances identified as versicolor, while it appears that on the basis of the plot of petal length versus petal width, they should be identified differently. So through visual examination shown in figure 8.10, we have drawn boundaries which seems to separate the three species pretty reliably based on just two of these attributes, like for instance the petal length and petal width. So consider the example of sample 50 that is classed as versicolor by Anderson and lies on the versicolor side of the species boundary. So therefore, the clustering algorithm should have put this sample in the versicolor cluster, but the simple K-means put this sample in the Virginica cluster as shown in the figure 8.10. So in figure 8.11, so if we look at petal length and petal width, sample 50 looks like versicolor, but if we look at sepal length and sepal width, it looks like Virginica. So the point is that the clustering algorithm takes into account all attributes except for class attributes when when clustering samples. So when all flower dimensions are taken into consideration, the simple K-mean algorithm puts sample 50 in the Virginica cluster, not the versicolor. So in contrast, recall that for our decision tree classifier, it made decision only on the basis of petal length and petal width measurements. So it did not consider sepal length and width in the classifier.
Identification of centroids for each cluster. The centroid is the center of mass of the measurements for a particular attribute or particular cluster. Karon atong i-observe ang plot sa sepal length versus sepal width. So this information tells us something about the quality of the clusters formed. First, kay the farther apart the centroids are, the less nga ang clusters kay mag-overlap. So basically, the higher the quality of the clusters. Ikaduha, the lower the standard deviations, the more tightly ang samples sa cluster kay na-grouped around sa centroid, which also means high-quality clusters. Concept of within cluster sum of squared error. Para masabtan ang concept within cluster sum of square error, ato sang i-consider ang error for petal width. The petal width for sample 5 is 3.6. The clustering algorithm puts sample 5 in cluster 1. The petal width centroid for cluster 1 is 3.418. The error is simply the difference between these two values, that is 3.6 minus 3.418 is equal to 0.182. We do the squaring to make sure all the errors are positive numbers. Obviously, lower the error, the better the results of the run. Identification of the optimum number of clusters using within cluster sum of squared error. To decide about an optimum number of clusters for unlabeled data, within cluster sum of squared error plays a very important role. To identify this optimum number, we first set k is equal to 1 number of clusters and find corresponding within cluster sum of square error. Then we change k to 2 and find corresponding within cluster sum of square error. So ato lang siyang ibalik nga step para mag-increase ang value sa k by 1. Thus i-plot ang graph sa value sa k o sa corresponding nga cluster sum of square error. Classification of unlabeled data. Since na-discuss naman nato ang mga previous chapters na ma-apply ang classification sa data to make a prediction, ang importante nga requirement is labeled data. We can only apply classification if data is labeled. But in most of the cases, data may be unlabeled as it is a very costly affair in terms of manpower hours to prepare labeled data. Then the question arises, is it possible to apply classification on unlabeled data? The answer to this question is yes. It is possible to apply classification on unlabeled data by following some intermediate steps. Of course, we cannot directly apply classification on unlabeled data, but we can apply the clustering algorithm on this data to make clusters or groups based on input attributes. So these clusters can be added to the dataset and to set it as a class attribute or as an output attribute to make predictions by using classification algorithms. Adding clusters to dataset. Once we have determined the optimum number of clusters, we can group the samples into these clusters. And then we can come up with cluster names like say cluster 1, cluster 2, cluster 3, and so on, and can add it to our dataset. To add clusters as pre-process tab, upload the iris dataset and then select no class. We choose this option because we don't want Weka to assume any of the attributes as a class attribute. To add attribute to hold the name of the cluster still on pre-process, then go to choose, then select the add cluster filter, but do not apply the filter yet. So take note, make sure that no class is still selected or you won't be able to select add cluster. So as what I've said earlier, that make sure that no class is still selected or you won't be able to select add cluster. Okay, so applying the classification algorithm by using added cluster attribute as class attribute. We start this by hopping over the pre-process tab and removing the class attribute, which we do not want J48 to use when building its tree. Now we just go over to classify, choose J48 with default settings, and run it. Okay, so now by right-clicking on the model, we get a visual depiction of the decision tree generated by the classifier as shown. So pruning the decision tree. Pruning is actually used to simplify the tree because normally J48 creates the branch of the tree if there are a minimum of 2 instances to follow the path. So we can consider the number of branches by increasing this number so that branch will be created only if more than n numbers of instances follow that path. So increase min num object from the default value of 2 to a value of 10. So what this means is that J48 will prune the tree that it builds so that no leaf at the bottom of the tree will have any fewer than 10 iris samples. So as a result of increasing minimum number object from 2 to 10 is shown. Note that we don't have a few additional misclassified samples, but we have also greatly simplified our rules. So we have performed clustering on Fisher's iris dataset using Weka, and in the next section, we will implement the same concept using our language.
Clustering in R using simple k-means. So the first step is to loading the dataset. So we will first load the iris database to perform clustering. Since the iris dataset is widely used, the current community has already provided a dataset in R-based data, and we can immediately start using the in R. So the following command to load the dataset will be used as str iris. So in this figure, 8.26 shows that the data set contains 150 observations and 5 variables such as sepal length, sepal width, petal width, and species. So the following command converts the data set into a data frame and its output is shown in figure 8.26. So step 2, removal of class variable from dataset. So out of these 5 attributes, four or of our attributes are quantitative and one attribute or species is categorical. So therefore, to perform clustering, we will remove the species attributes from the data set and save it in a different list for a later use by the following command. So the species as list iris species and the unlist species. So after running the command in the figure, above, running the command above commands, the fifth attribute, which is species, gets removed. So now the iris data frame consists 4 attributes that it is shown in figure 8.28. So now we will apply the k-means clustering in the iris data frame by specifying the number of clusters to 3 and number the iterations of to 20 as given in the following command. So the output after running the commands in 8.29. So from figure 8.29, it has been observed that the clustering algorithm has identified 3 clusters such as 1, 2, and 3. So the algorithm has put 62 samples in clusters 1, 50 samples in cluster 2, and 38 samples in cluster 3. So we already know each class of iris dataset consists of 50 samples. After analyzing the result shown in figure 8.29, we can observe that the 50 samples of one class has been identified correctly and 12 samples have been classified wrongly and assigned to a different class. So the cluster size can also be identified using the following command at is shown in figure 8.30. So similarly, the centroid of clusters are shown in figure 8.29 and can also be identified using the following command. So the output of the following command is shown in figure 8.31. So in figure 8.32 shows that the plot between petal length and petal width are after clustering using the following command: iris cluster and iris cluster. So the plot of column iris clusters means key means result will 3 clusters. Comparisons of clustering results with the original dataset. So let's cross-validate the results of clustering with original dataset. So it can be done using the following commands. So table, iris, clusters. So the output of this command is represented through a confusion matrix in this figure 8.32. So as we can see, the data belonging to the Setosa species got grouped into 2 clusters, versicolor into cluster 3 and Virginica in cluster 1. So the algorithm wrongfully classified 2 samples belonging to versicolor and first samples belong to Virginica. So adding generated clusters to the original dataset. So the graphic expressions of cluster can help us to evaluate whether the result makes sense. If we determine that it does, we can also include the result of clusters analysis in the original dataset. So thus we bind the results of clustering analysis with the original dataset using the following command in 8.34. So it adds the cluster to original dataset. Apply G48 on the cluster dataset. So the following commands are to run apply to the decision tree and classes predicted by its application in this figure 8.35. So we will type library party, then the iris clusters converts integers data type to factor data type. So target cluster, sepal length, sepal width, petal length, petal width. So and the CDT C3 target iris clusters, it is the applications of a decision tree. So in the table predict CDT iris clusters, it is a predictions of classes. So the confusion matrix in this figure 8.35 shows that the 50 instances of Setosa are classified correctly and 16 other instances are classified incorrectly.
So that's all. Thank you. Thank you everyone for listening and God bless.